Hey everyone, and welcome. Today, we're diving into a really fascinating new way to think about building and controlling complex AI. We're talking about a fundamental shift, moving from what's called token time to something called episode time. It's a whole new engine for AI systems.
So let me ask you this, because you've definitely seen it happen. You've got a super powerful LLM working on a complex problem, and then suddenly it starts repeating itself, or it gets fixated on a really bad idea, or just, completely loses the plot. Why? Why do these incredibly intelligent systems get so easily thrown off track?
Well, the core idea we're exploring today is that the problem isn't the AI model itself. Nope, it's the clock we're using to measure its thinking. And for complex tasks, that clock, it's just fundamentally broken. So here's how we're going to break this down. First, we'll talk about why the current clock is so wrong. Then, we'll introduce the new building block for all of this, the semantic cell. After that, we'll look at the engine that actually runs these cells, learn how to check in on the AI's state, and then finally, see how this all comes together to turn AI chaos into something we can actually control. Okay, let's jump right in. Section 1, the wrong clock. Let's really pull apart the way we've been thinking about AI progress up until now. So right now, the whole industry pretty much runs on token time. We basically measure an AI's work by counting how many words or tokens it spits out. The chef analogy here is just perfect. It's like judging a chef by how much flour and sugar they've used, not by the amazing cake they baked. The move to episode time is all about focusing on the finished dishes, the meaningful, completed steps in a reasoning process. And this gets to the absolute heart of the issue. An AI can write 1,000 words just spinning its wheels, going nowhere. Or it could generate 5 critical words, like a specific command or a key insight that totally crack the problem. The amount of text it produces and the actual progress it makes are just dangerously out of sync. So if token time is the wrong clock, what's the right one? Well, that brings us to section 2, where we get to meet the new, true building block for these systems. The new clock, episode time, isn't measured in seconds or words. It's measured in what are called coordination episodes. And look at that definition. An episode isn't about how long it takes or how much text is generated. It's about completing one single coherent thought from the moment it's triggered all the way to a stable, useful output. Okay, so a coordination episode is like one whole step in a recipe. But what are the individual ingredients, the actions that make up that step? They are built from semantic cells. And this, right here, is the absolute core of this entire framework. A semantic cell is the tiniest, reusable piece of a reasoning process. Think of it like a specialized microtask. You might have one cell whose only job is to check a document for contradictions. Another one just retrieves a piece of evidence, and another one just validates a piece of code. Each cell has one, and only one clear purpose. And this is what's so powerful. This is what turns AI development from a kind of mystical art into a real engineering discipline. Every single semantic cell is defined by these 8 components. It has a clear intent. It knows exactly when to start and when to stop. It has clearly defined inputs and outputs. It even accounts for things like tensions it needs to balance. This level of structure is what finally lets engineers monitor, debug, and understand an AI's thought process with real precision. Okay, so we've got these incredible building blocks, the semantic cells. But how do they actually, get put together and get to work? That brings us to section 3, the 4 runtime primitives. This is the engine that makes it all go. And that engine runs in 4 very clear steps: trigger, routing, convergence, and composition. This 4-step dance is the life cycle of every single reasoning step, every single coordination episode. Let's break that down real quick. First, triggering is like a scout. It scans all the available cells and figures out which ones might be useful right now. Then, routing is like the general. It makes the final call and activates one or more of those cells. While a cell is running, convergence acts like a supervisor, watching and waiting for it to produce a stable, finished result. And finally, composition is the artist. It takes all the finished outputs from the cells and weaves them together into the new, updated state of the system. This cycle is the very heartbeat of the reasoning engine. Now let's zoom out a little for section 4. If the cells are the Lego bricks and the primitives are how you snap them together, how do you see what the whole machine is actually doing? Well, you look at its control panel, the episode's state. So instead of trying to make sense of a long, confusing string of text, an engineer gets this beautiful, clean dashboard with 6 key readouts. They can see exactly which cells are active. That's what the AI is doing.
They can see what tensions it's balancing, like speed versus accuracy. They see what it knows, why it chose a certain path, and what it has already produced. This is what true observability into an AI's mind looks like.
All right, so let's get to the payoff. Section 5, from chaos to control. Why does all this reorganizing or thinking around episodes and cells, why does it actually matter in the real world?
This slide highlights a really critical distinction. Local convergence means a single cell did its job. It finished. It produced a stable output. That's a success, but it's a small one. Global task correctness, well, that's the real prize. That's making sure the output is actually the right answer for the whole problem.
And this is the whole game right here. An AI can confidently complete a step, arriving at a conclusion that is completely wrong. It can be perfectly stable on a terrible idea. The entire purpose of this framework is to give engineers the tools to see when this is happening, to detect when local success and global failure are drifting apart. And because the system state is so clear, we can finally start putting names to these common AI failure modes. We can now detect things like an attractor loop, which is when the AI is just stuck on repeat, or an asymmetry block, where it latches onto one idea and just refuses to consider anything else. These aren't mysterious glitches anymore. They are specific, diagnosable engineering problems that we can actually fix. Ultimately, what this all boils down to is a massive shift. We're moving away from treating LLM behavior like some unpredictable, mysterious black box and toward managing it like a structured, observable, and controllable engineering system. We're finally building a true runtime for reasoning. This quote from the source material just captures the whole idea perfectly. Token local control stabilizes generation. Episode boundary control stabilizes coordination. In other words, controlling the individual words just makes sure the AI sounds fluent, but controlling the episodes, that makes sure the AI is actually thinking straight. It's the difference between stabilizing language and stabilizing reason itself. So I'll leave you with the question on this final slide. This whole framework really challenges us to ask, is the next big breakthrough just about building bigger and bigger models? Or is it about creating the blueprint for a true reasoning engine, one that thinks step by meaningful step? Thanks for joining this explainer.